All right, so we're going to be doing experiment 3.1, and experiment 3.1 has this research question, which may take a little bit of explanation. But what happens to an aluminum can when the atmospheric pressure is removed from inside of it? So what terms do you think we might end up having to define? Precisely, yeah. So this is all in the purpose section of your lab report. And then in the background, most of you have this by now, but just to be clear, the background, you're going to define any terms that we needed to define in order to understand the experiment. And I point out which ones you need to do in class. One or two of you actually added a term, and I thought, wow, that was a really good one to add. So atmospheric pressure. Could somebody look that up in module 3 of the book?
It is the pressure exerted by the atmosphere on all objects within it.
Very good. The pressure exerted by the atmosphere on, you said all objects within it or under it? What did it say?
All objects within it.
Great. On all objects within it. All right, so here's a really stupid example. Look at my face. Why is that happening? Yeah, because I'm exerting air pressure from the inside on my cheeks, and they're expanding outward. So have you ever like put a vacuum up to your mouth when you were a kid or something? I'm not advising that you do this, but just in theory, if you took like a powerful vacuum and like took the hose and like put your lips around it, what do you think would happen?
Your tongue would come out.
Hopefully not.
It'll try to suck your face in there.
What do you think would happen to your cheeks? Maybe they'd go in? So those are examples of air pressure. In the first example, air pressure going outward, which is stronger than any inward air pressure. In the second example, it's a lack of air pressure on the inside, and then the air pressure on the outside is actually what's, believe it or not, pushing your cheeks in. So that's what we're talking about when we're talking about atmospheric pressure, is basically just pressure from the air. And you might be thinking, well, wait a second, air is really light, so how is it exerting pressure? The atmosphere is very tall. It actually goes on for miles. So here you are on the Earth. And then you have miles of air on top of you. And what is gravity doing to that air? Yeah, it's pulling it down. And so while air is very light, it's particles that are small and spaced out far apart from each other. If you have miles of it, then the weight of those miles of air molecules and atoms are going to, mostly atoms, but they're going to bear down on you with a certain amount of weight. So how much, just like on average at sea level, what is the average atmospheric pressure on Earth? And it says so in the book. It says what it is. I believe it's 14 point something pounds, right, per square inch? 14.7 pounds per square inch. Now, 14.7 pounds per square inch, that's actually kind of a lot. Because if you think about, like, if you hold out your hand, how many square inches are on your hand?
A lot.
Yeah, it's actually a lot, because, like, let's say it's 6 inches this way times, I don't know, 4 inches the other way, that would be like a little less, that would be somewhere around 20 square inches, just on the surface of your hand, maybe. So 20 times 14.78, so that's like, what, 280 pounds of air pressure on your hand. So when you're holding your hand up, you know, it's like you're holding out, it's like you're actually lifting 100 or 280 pounds, right? It is, except there's something else going on too, which is that the air pressure is all around, so you have air pressure pushing down, and you have air pressure that comes around your hand and pushes up from underneath too. And so so basically you have atmospheric pressure kind of everywhere. It's on all objects within it, and it's pushing from many different sides. So if you were to take, I don't know, let's say you had a sheet of paper over covering like a fish tank, like it's totally sealed, and there's a piece of paper sealing top of a fish tank. Would it make sense for that paper just to sit there flat, stretched across the fish tank? Yeah, but what would happen if you, again, well, let's say that the sheet of paper was, I don't know, 12 by 6, so like 72, roughly, let's say 70 times 14. So
980.
980, thank you. So you have about 980 pounds of air pressure on that sheet of paper, believe it or not. And but it's still just sitting out there, and the reason is because you also have, an equal amount of air pressure roughly on the inside, because there's air that was pressurized inside the fish tank. So what would happen if you sucked the air out of the fish tank and still have that seal of paper?
It would fall.
You think so? That's basically what we're asking in this experiment. What we're going to do is we're going to take, and I would include both of these things in your background. I would include the definition of atmospheric pressure and the fact that the average atmospheric pressure at sea level, which means the elevation of the sea, is 14.7 pounds per square inch. And that amount of atmospheric pressure is actually called 1 atmosphere. Fun fact. So you can include these things in your background. Now we need a hypothesis. And I'll describe the experiment so you can make a better hypothesis. We're taking root beer cans. We're putting a little bit of water inside. Just a little bit. And we're going to boil that water and let the water evaporate and push the air that's inside the can out as steam. So remember, hot air rises, and so as you evaporate this water, there's actually going to be a current of air forcing the atmospheric pressure out of the can, because the air that was pressurized that's inside the can is being pushed out. So then the question is, when we reduce the atmospheric pressure inside of the can, if we then put it in an environment where air can't enter it at all, like where it's just kind of sealed off a little bit, and we're going to actually kind of amplify that a little bit by putting it in cold water. We're going to take some tongs and take the can, once the atmospheric pressure has been largely removed from it, turn it upside down and dip it into cold water. What do you think is going to happen? All right, so I saw one person say the can is going to crumple. What else?
Well, is the opening gonna be like in the water?
It's going to be in the water, yeah.
Probably crumple.
Probably crumple? What's that? All right, so let's find out. We're going to have to empty a bunch of cans, so if anybody wants to chug any last or whatever. I think I'll actually have a sip or two. I've not been here forever.
You want me to drink this? No, I thought you just meant to pour it out. But I got them. We can drink it this time.
So let's take all the empty cans, and if I could have a volunteer to rinse them out, we can put them all in here. Okay, that's fine. You have another moment, so. And we don't really need more than one necessarily, but this experiment is better. You can finish it. If anybody isn't going to finish theirs, you can just go dump yours outside. I'm going to start heating up this griddle. Probably should have been doing that.
How does it taste like?
Alright, so empty cans. We can put them in this right here, and then if somebody's willing to go and rinse them out. And if you need to pour yours out, you can just do that out there. Oh, look at that. It's a very satisfying sound.
It has 120 calories. 1 can.
Man, I forgot how good this stuff is.
Pour it out, Sarah.
Dale doesn't like it.
Oh, Sarah. Total sugar is 46 cents. Ew, no. I don't want it.
That's fun. Yeah. No, three. Two. Not that fast. Only drink two.
Okay.
I'll take another.
Then we got like one more coming, and then if somebody can rinse them. And when you rinse them, it'll be good to actually, yeah, just rinse. I'll put the water in. Any volunteers to rinse them out? Thank you, Sarah. So yeah, sorry, it's starting to smell a little funny up here. I apologize for that. So while we're waiting,
Hurts so bad.
your stomach hurt. How many of you had?
I only drink two. Only two. Only two.
We can start looking at the module a little bit, maybe. Although I do have more setup I can do, and I can explain what I'm doing with it. So I'll move this camera. All right, so here's where the experiment is. And I'm also going to get, do we have any more of these tables? Probably not. I'll just put it over there.
Where's the waiting table?
Yeah.
Yeah, there's a corner.
In the corner.
Over here.
Oh, perfect.
How old is that thingy?
My mother replaced me.
I've probably been using it for at least like 5-6 years, maybe longer, maybe 7, maybe.
Did you actually use it to cook stuff or just for this experiment?
Just for this experiment, maybe one other.
Eggs and beers and sausage.
Do you think it was worth buying it?
It was actually pretty cheap.
Oh.
I think I got it for like 20 bucks. Yeah, but the thing is, it's because it's cheap, it actually warps the plastic under its own heat. So parts of it have melted just by turning it on and using it the way you're supposed to. So that's what happens when you buy cheap Walmart stuff sometimes. Okay, so to prep this other part of the experiment, I'm going to put ice. And this is an experiment that everybody can participate in because it's very satisfying. I'm not sure if we have enough cans for everybody, but we're pretty close. Because I think, we have like 13 people in this class. Now, if someone could read the setup, I can't remember why I have 2 bowls. I think I put ice in both. Thank you. I'll take it up here. Make it fix. Okay, so
It's not rinsed.
yeah, that's okay. I'll rinse it a little bit.
Ooh,
That's probably fine. I won't worry about it. So I'm going to put all these cans here. Oh, someone's already crumpled.
Why is it sizzling?
It is wet.
Yeah.
Oh. I didn't think about that.
Yeah. It's okay.
No, I didn't smash mine.
So we got 6 good ones. All right, so I'm going to put a little bit of water in them. And if someone could start reading the experiment, that'd be great. Just read everything, and I'll tell you to skip ahead or not.
Supplies? Supplies.
Skip supplies.
Alright, procedure. Would you like to go first? Would you? Yeah, I would.
Go.
You want to go?
Put a small amount of water.
Put a
in
small
each-
amount of water. Oh, wait.
You should use only enough to cover the bottom of the can
Why do I do
with
it?
a small amount of water. The more water you use, the longer the experiment will take and the less dramatic the effect.
Alright.
Okay, next one, please.
Place the 2 aluminum cans in the frying pan so that they stand up.
So we are using how many aluminum cans?
6.
6. Yeah, just because we can, which is sort of a pun, I suppose. Didn't mean it to be. All right, I think I'm going to turn this sideways. Okay. So they are standing up. They are getting ready to boil.
Put the frying pan on the stove and turn the heat up to high and let it heat up.
Yep. So an obvious supply difference from the book is instead of a. Oops, that's not good. I think it's still got enough water in there. Ah, dang it. No. Okay. Yeah, so we're using this instead of a stove, obviously, and no frying pan,
Does
because...
that water already evaporate? Like all
Yeah, I think there is some evaporating already. Alright, next, please.
While you are waiting for the water in the can to heat up, fill each bowl half full of water. Place a few ice cubes in each bowl so that the water becomes ice cold.
Alright, I'm gonna go a little excessive on the ice cubes. You know what, just for fun, I'll use the tongs.
Oh wow.
As I can. That's probably good.
Begin his head.
I got plenty more of them. Alright.
Why does that look so fancy? To be using tongs to get ice.
Yeah, I guess it kind of does, doesn't it?
Ooh.
They're not left.
So then fill this up. Good, yeah. So we're seeing the evaporation, that's good. And what's a possible error analysis coming from just the way it's evaporating? That's probably a little more than half, or whatever.
I'll like open the lid is.
Okay, yeah, so the lids are not all equally open, that's one thing.
Chemical?
Possibly, yeah, so not all of them are going to be equally rinsed. So that's another thing too, like the root beer, if there's more root beer in it, then it's going to evaporate a little bit differently, you know, because obviously the more water it is, you know, pure water is going to all evaporate, root beer will not quite as much. So if you had like a ton of root beer, it might have a different boiling point as well. So it might have a small effect. Anything else?
When you spill the two cans.
Yeah, that's another thing. So, and then a final thing I would imagine is like, do you think that this thing heats exactly evenly everywhere?
No.
Probably not. So there's a chance that some of these are heating faster than others, and right now, if I look at them, I see more steam coming out of this one than any others. So the result then is like, you know, I think they'll all have the effect we want to see, but there is a variation in the amount of atmospheric pressure we're going to have in each can. So some cans may crumple more easily if they do crumple, or do anything else that we might observe. There is something else that nobody guessed that it may happen. So yeah, we might see some interesting stuff, but they will not probably all behave identically for a few reasons. All right. So what's the next part of the experiment? Oh yes, that could be bad. Thank you. Is that in the shot? I don't think it is. I'll just turn it when the time comes, or move it. So what does it say after that?
Wait for steam to start rising out of the opening of each can. That will tell you the water inside is boiling continuously.
Okay, after that, because that's sort of happening now.
Once a steady stream of steam is coming out of each can, use the tongs to grab one can and place it upright in one of the bowls of water.
Okay. So if I recall, actually, we don't really need 2 bowls. I think they just want you to have 2 bowls for, you know, each of the 2 types of tests. Remember, what do we call it when we have a second test for the experiment where we don't have the variable going on that we're trying to, yeah. Bo, actually, how about that?
Oh, okay. It was called a control, right?
Very good, yeah, the control. So this one's going to have a control test. If our test is to see what happens when the can is turned upside down after the atmospheric pressure has been pushed out, you know, we're putting it in there with it upside down. What do you think a control would be? What would be a good control for this experiment?
Bring it right side up.
Exactly. We're going to take one of these cans and put it right side up. So if somebody wants to read ahead to that.
Use the tongs to grab the other can and place it upside down in the bowl of water.
Okay. So what I'm going to do, I'll do the first one. Everyone ready? 3, 2, 1. So one of 2 things generally happens with this experiment. Did it crumple?
No.
Okay, so with this one, the hypothesis wasn't right. But look what happens when I lift it.
Sucked in all the water.
Yeah.
I'm a big fan.
All right, so there's the first one. I'm going to get this one going again, actually, because that didn't rupture or crumple or anything like that. All right, so then my control experiment is just I take one and put it right side up, right? Okay, so I'm gonna put that in the other one. How about this one? This will be
Would
my.
another control be to put a can that hadn't been put on the burner upside down in the cold water?
I think that would actually be a good idea, yeah. I think that would be good to have that control as well. Good thinking. Yeah, so when I put this in right side up, is anything happening?
No, just pushing it up.
Yeah, not really.
Doesn't want to be there.
Alright, so these two I'm gonna put in the back, because we can use them again. Anybody want to try dunking? Alright, so you can go first, and then you, and then... We could just kind of have everybody, I think. Because anything that doesn't crumple, we can put back on the assembly line of destruction.
Should we put like those two cans that didn't do anything, should we put those in the lab report?
Let's record it this way. So, we're doing, excuse me, I'll hold my breath.
Alright, no, camera.
Okay. Let's make a chart. So, let's say we have our control test. And instance number 1 of that, we'll just say no effect. Like nothing crumpled, it just kind of sat there. And I'll say the variable, how about that? Test 1 sucked about a can full of water, or as deep as it could go pretty much. Maybe not a whole
Control
can.
test is the one where you put it upside down.
The control was the one where it went right side up, and then the test is the one where we actually turned it over. So the second one we did where nothing really happened, that was control. Alright, Sarah, you can go. Thanks. Trying to make sure that the bottom of that griddle isn't completely warping and melting, but it probably is. Alright, let's see if it sucked a bunch of water out. Yep. Alright, hey, the class just in?
Yeah.
Alright, well, wanna watch me do 3 more just real fast? Thanks, Sarah. Alright, last 3. Okay, still sucking water.
Are there any crumpled people?
Oh yeah. Oops. Okay, now let's try this one. Yeah, still crumpling, or not crumpling, just sucking. And you can read about why. This actually is proving the same thing that crumpling would have proved. It's just doing it a little differently. It's less interesting. Okay, so that was, we did a total of 5 that all just sucked water. All right, thanks everyone. Yeah, so the control is the only one that didn't. So we did 1 control test and nothing happened, and we did 5, variable tests where it had the same effect. Thanks. Have a good lunch.